Test. All right, Peter, can you hear me? Peter, can you hear me now? There. Peter, I can see you now. Can you hear me? Yeah, you're on. Can you? I can hear you.
Welcome to WebEx. Enter your access code or meeting number followed by pound. Enter your attendee ID or the numeric meeting password followed by pound.
Peter, can you hear me? Peter.
I can't hear you. I can see the initials on your screen, the SG.
Can you hear me on the phone?
How about now? My speaker was turned all the way off.
Okay, can you hear me now?
I can now, yeah.
Okay. I'm not sure. I'm on the phone now. Not sure what happened there. At any rate, good morning.
Morning.
Getting warmed up now?
Yeah, well, I mean, obviously I'm used to using Zoom a lot these days just because, you know, for lecturing and things like that too, but, you know, WebEx is new to me, so yeah, I don't know what it is with Zoom, but for some reason every time I log onto it, my speakers are set to almost zero, and I have to go in and manually adjust them. And I guess here it's the same thing. It was just all the way set to zero, so I had to find the right controls. And
okay. I wonder if I can try back to the internet audio instead of my phone.
Probably so. Now that I've got my stuff together.
I was just kind of freaking out for a minute. I want to make sure that we could communicate. Before I do that, Peter, I just wanted to ask a simple question. Do you pronounce your last name Ernez or Ernez or? Sorry.
It rhymes with furnace. Like in your house, you got a furnace that heats your house. It rhymes with furnace.
Okay, but I mean, do you pronounce the H, or, you know, depending on?
Yeah, you do pronounce the H. It just rhymes with furnace.
Okay.
My mother was a kindergarten teacher at some point, and so, you know, she would tell her class that her name rhymes with furnace, and then they would call her Mrs. Furnace for the rest of the term.
Very good. So how are you doing these days?
Well, I mean, it's obviously a loaded question. You know, we've been doing the shelter in place for a month and a half now. So, I mean, I don't know. I'm okay. It's also here at the University of California, we're on a ladder system, and so we go up for merits and promotions every 2 or 3 years. And so it's sort of in my cycle right now. So there's kind of this like frantic push to get some of the publications wrapped up and finalized here. And so that always adds a little bit of extra stress to my life once every 3 years. So there's some of that going on. You know, I've got family at home who claim to be bored, and I don't know what bored looks like because I can't remember the last time I've ever been bored.
Right, right. It's amazing. I mean, it seems like there's more meetings now. Of course, everything is Zoom, and you get tired of staring at your screen all day. But things haven't slowed down, really. We're fortunate enough. I mean, we live in the country, a small farm, 35 acres around us, so we're pretty well secluded. And, we have a warm house and plenty of food, and, we're okay. Unlike a lot of other people. And we'll get through it. But it's, I don't know, it was a novel thing for a while, but this could go on a long time, and that's going to be a different situation. That'll be hard.
Yeah, and California, of course, was kind of started this before a lot of the other states did, and so California's been doing okay. But it's like, now everybody else is trying to open up, and it feels like California is still going to be progressive on this and still going to stay locked down until everybody else has gone through their boom bust. I don't know. I'm really curious to know how this next month is going to go. If we're going to see these big flare-ups around the country, different places.
Right, right. Yeah, I just, and this happened for a few weeks, so that, that's okay. It's kind of a novel thing, but the patience of people is, they're not going to do this. It just isn't going to happen, and it's already kind of breaking down. But scary future.
I definitely have more staying power than a lot, and I know that on some level that's a privilege. Having a like what you're describing there too, having a job that I don't really fear that I'm going to lose my job. I mean, it's possible that, and I don't know, on some level, I'm sure it's likely that in some way our salaries are going to get cut. Either we're going to have to chip more into retirement, or our salaries are going to get cut, or both. Those kind of dynamics. But having 80 or 90% of my job is still better than having no job.
Right. Exactly.
Yeah. So I realize that I live in a very different reality than a lot of other people when it comes to job security, things like that. So I try not to be too whiny about anything.
Right. Yeah, we thank our lucky stars every night. So far, so good for us.
So you're in Wisconsin?
Yeah, University of Wisconsin-Madison. We live outside of Madison, but yeah, you ever been here?
Yeah, I was there for I guess a meeting a year and a half ago in November. I was in Madison, and I haven't been there much. I guess I've been there once or twice before. I grew up in North Dakota. I went to school at Luther College in Iowa, so
really?
it wasn't too far away.
Yeah.
I've obviously got college friends from the Madison area, and I just hired a postdoc from Madison who's finishing up at UW. So.
Oh, really? And what program?
Well, she's coming from, I don't know if she's coming from ecology. So we're working on a food web problem here in the local California Delta.
Yeah.
I don't know how familiar you are with California, but there's a sort of like an inland delta in between Sacramento, Stockton, and San Francisco Bay, and it's like the central water hub for all of California. So it's very, very important for the economy, very important for California in general. But that means there's an awful lot of forces on it too, and so ecologically it's collapsing. And so there's been so we look at it from the carbon cycling side of it, and of course the Endangered Species Act is the big piece of policy that's driving everything there. So there's native fish that are on their way out, and probably are going to become extinct no matter what happens, just because of climate change. But you know, but for right now, that's the big driver. And so food web dynamics is one of the aspects that gets a lot of funding, a lot of attention. So we kind of tapped into the carbon side of the lower food web, and so that's what she's coming out here to do. Is kind of a project that bridges the gap between ecology and biogeochemistry.
Oh, okay.
Yeah, and so I've got a
We
collaborator.
probably know-
Yeah, so I got a collaborator here. What's that?
I was gonna say, we started dropping names, we probably know some people, you know,
Maybe so.
yeah. Well, I like Madison. It's a nice area.
How long have you been there?
Probably 32 years. So.
Yeah, it goes fast. I got to Davis in 2002, and I mean, it's like 18 years just like that.
Yeah, right. No, I've you know, I'd worked for Wisconsin Department of Natural Resources for a number of years, and again got this fellow position with the university. A lot of people at DNR have joint positions at the university, and so now I don't have my DNR position, and I just have this fellow position, and I also, you know, one-third researcher time with space science and engineering on campus. So just right.
Peter and Steve, just letting you guys know I'm here and I'll handle questions in the chat.
Okay. I'm actually going to try. I'm on the phone. We had a little audio problems. So what's our time? Oh, we're about ready to start. I'm not going to switch then. Is the clarity of my voice okay?
Yes, I can hear you.
Yep. Seems good.
I can hear you too, Peter.
That's always good too. I mean, I do have some ability to turn up my microphone if I need to, but if it's fine, then I'll just leave it alone.
Yeah, you're fine. Loud and clear. I would just say present in slideshow. Right now you're in the full screen.
Yeah.
I mean, you're not in full screen.
So will that work?
Yes, perfect.
Perfect.
Ooh, that's a pretty picture.
Nice.
Yeah, you get a lot of pretty pictures from space, is what I've learned by hanging out with these people.
Okay, I'm gonna mute. Steve, you may have to be ruthless with muting people.
We'll see. So Peter, we might not start exactly on the hour. We'll give people tend to dribble in here a little bit. It'll probably be a few minutes after.
That's okay. It gives me a chance to wake up a little bit too. This is like virtual jet lag.
That's a good one. Can I use that?
Sure.
And I'm going to stop my video to reduce distractions here. Hello, everyone. We're going to give everybody just a couple more minutes and we'll get started here. Okay, I think we'll go ahead and get started. I hope everyone can hear me. Good morning, good afternoon, or good evening, as the case may be. My name is Steve Greb. I'm the director of the GEO AquaWatch, your water quality community. I'm going to ask everyone to please put their phone on mute or their computer on mute. At any rate, as I said, I'm the director of GEO AquaWatch, the community of practice. And please, I would ask before we get started to make sure you're muting yourself. Today, our speaker is Peter Bermez. He received his master's and PhD in chemical oceanography at the University of Washington in Seattle, and did his postdoctoral work at the University of South Carolina in Columbia before landing his current position at the University of California, Davis in 2002, where he's now a professor of hydrology and aqueous geochemist. Peter uses biomarkers, primarily ligands, in conjunction with several other bulk measurements to characterize sources, processes, and fates of organic matter in rivers out to the coastal ocean. In particular, he's interested in how the river chemistry maps back to land use, landscape sources, and processes in constant change. So this is fascinating work, and we're excited to hear from Peter today. So with this, I'll turn it over to Peter.
All right, thank you. I've obviously become a lot more familiar and comfortable with lecturing to a screen than I ever imagined that I would be in this last quarter here, as I imagine a lot of other folks have too here. So it's a little bit different format here. Just sitting in my office. I don't know if I consciously put a California map here in the backdrop, but you know it seems to fit pretty well. Anyway, I thank you for the invitation to come and present this work. My talk is really split into two different parts here. The first part here, I'll be talking about a scoping study that we started back in 2014 to design a field campaign for NASA. And this is kind of a ground roots effort. NASA had put out a call, I think kind of wanted to do something different where the field campaigns were designed from the bottom up instead of the top down. And so the idea was to put out a call and let scientists put together their ideas for what they think is important to study. And if it rises to the top, then NASA will go ahead and fund it. And so Arctic Colors is one of those kinds of projects. Right now, Exports is another one of those field campaigns that was started from the ground up. proposed by a group of scientists, and eventually it worked itself into a full-blown field campaign. And so right now Arctic Colors is on that same kind of a track. And so the first part of this talk is about Arctic Colors, sort of the field campaign as we envision it. And then the second part of the talk is a currently funded project that we have by NASA that we call pre-Arctic Colors. And that's the idea that there's, you know, even without going into the full-blown Arctic Colors field campaign here, there's some work that can be done ahead of time and to try to prepare for that. In particular, one of those things is that the Arctic is changing so rapidly that, you know, that we need to be out there getting some sort of benchmarks for the current status, the current state, so that we have something to compare to later on when we get into Arctic Colors. And so that's the second part of the talk, is getting into a little bit of the research that we've been doing with that. Nothing's really conclusive on that at this point here, because we're still in the middle of the project, but I'll show you teasers of the things that we've been coming up with. So the Arctic coastal zone is obviously very vulnerable like the rest of the Arctic. It's also very complex with lakes, streams, wetlands, permafrost, rivers, lagoons, you know, areas of boreal forest, woody places, estuaries, all modified by snow and ice. And it's such a complex environment, and it's such a hard place to get to, that it's very poorly characterized or incompletely characterized. I'm never quite sure how to say that. I mean, poorly implies that somebody's up there doing bad work. So I don't want to imply that. It's just that it's hard to get up there and do the kind of work that you're trying to do. And so these pictures all kind of show some of the different environments that you have to have. And you can imagine that looking at any one of these environments here involves a lot of research, a lot of expertise here too. And so no one person is going to have the expertise to do it all. And so Arctic Colors is an idea of trying to bring people together who work primarily on ice, working with biogeochemists, working with oceanographers, working with pastoral ecologists, marine ecologists, things like that, trying to bring people together here to try to work on all the complexities of this environment. And then NASA. Well, I mean, you can imagine that it would be really hard to get good spatial coverage in a region like this. And so the idea of bringing NASA into this is really on the upscaling part, both temporal and spatial, where, you know, we can get data on the ground there, but it's really hard to get the coverage that you need for both spatial and temporal coverage. And so we want to bring in the NASA piece here, the remote sensing piece, to try to tie it all together. And of course, we've got satellite data that goes back to 1997, CWIFs. And so the idea here is that we have the opportunity to do hindcasting as well. And so Arctic Colors is the idea behind Arctic Colors is that it will run, once it gets started, it'll run out to maybe 2030, maybe even into the 2030s. And so by the end of this field campaign, we might have 30 to 35 years of remote sensing to be able to kind of really get a handle on what's happening in that coastal zone. So Arctic Colors aims to quantify the coupled biogeochemical ecological response of the Arctic nearshore system to rapidly changing terrestrial fluxes and ice conditions, both in the context of short-term and long-term change. So we started with this plan back in 2014 when we developed a science plan in collaboration with the broader community. We brought in international collaborators, obviously folks who have expertise in areas that we don't. We have a project website. The link is listed here. You'll see that link. I guess it's down here as well. You'll see it at least one more time here if you want to go. There's a full-blown science plan that we put together, and it's been revised a couple of times here. That's on that website that you can download to get a lot more information. And we've done a lot of meetings, town halls, workshops, things like that to try to promote this. At the end of the day, Arctic Colors won't go without community support. So I'll start plugging now that if this is something that you want to go, please contact NASA program managers, and I'll give you some people to contact at the end here. The more attention and pressure they get from the scientific community, the more likely this is to go. Right now, the idea is that once exports is winding down, Arctic Colors will wind up, but we don't want to take anything for granted, because as we know now, this court, anything can happen. So we still need community support for this to go. Three drivers, I think, that motivated us to put together this field campaign is the context of vulnerable Arctic. My personal action of doing biomarkers from space. And then focusing on this nearshore environment. I think there's been a lot of field campaigns in the past, but they tend to go on big boats, and the big boats can't get in to the river mouths and to the coastal zone. And so one of the things that we were specifically trying to do with this is have a field campaign that's really right at that land-ocean interface, getting in close to the near shore. So it's not something that you can do from big boats alone. You gotta do a whole combination of field work, field campaign things to be able to get at this near coastal zone. So we had our workshops, we submitted our drafts, we've gone through the science panel. The science panel, I guess the overarching comment was that this represents an important and timely opportunity for NASA because of the rapidly changing Arctic environment. Community workshops in 2016, revisions in 2017, multiple presentations at different conferences, town hall meetings, things like that, and then ultimately the public release of this Arctic Colors Science Plan. This kind of gives you a snapshot of what we're trying to get at in this near coastal environment. And this picture is a little bit unevenly weighted toward the water side of it. We are interested in wanting to know what's happening in the delta region, the estuarine region, sources of terrestrial materials up on the land. So if we were going to draw this figure here and sort of make it a little bit more in line with what we have envisioned for Arctic colors, you would slide this landscape a little bit more into the middle here. But there's a lot of action that's going on in the water column that we wanted to try to catch with these diagrams. So as we have it scoped out, there's really 3 different thrusts to this: the effect of land on nearshore Arctic biogeochemistry, the effect of ice on nearshore Arctic biogeochemistry, and the effects of future change due to both warming land and melting ice on this nearshore Arctic biogeochemistry. So the land things that we're looking at I think are probably pretty intuitive here, looking for changes, or identifying first of all freshwater, carbon, nutrient, and sediment fluxes to the coastal zone, but then changes due to climate change or other anthropogenic drivers here that change the riverine and groundwater inputs. We want to characterize the passage of material through estuaries and gradients, and this is sort of a little bit of what we get at with our pre-Arctic colors research that I'll talk about on the second part of this talk. Coastal erosion is obviously a big topic up in the Arctic, and here's an example of a house that's disappearing, but there are whole villages that are essentially disappearing into the Arctic Ocean from coastal erosion, thawing, permafrost. All these things, aside from the human tragedy or the ecological tragedy involved, are dumping materials out into the coastal ocean. So we're interested in how much and what these materials are doing. And then, of course, the changing fluxes, looking at the magnitude of seasonal changes, interannual changes, things like that. There's obviously been some record warming periods that have been happening up in the Arctic now, and just weird things where you get this big warming in March and then everything freezes over again in April. That's something that happened in 2019 as we were trying to figure out how do we get ourselves in there to get at get to the kind of the height of the spring freshet for doing our sampling. Well, it's hard to know that when you get record warmings and things are changing so much. And then looking at the effect of ice on the nearshore biogeochemistry. Ice obviously changes a lot of the flow of the water and impacts how quickly things can get started up in the springtime, and there's a lot of impacts on the light that gets into the waters, so there's different things that we need to be aware of with the snow and ice. I'm not a snow and ice person. I did grow up in North Dakota, so I'm familiar with snow and ice. But at least not from a research perspective. That's not my area, which is one of the reasons why we want to bring together lots of people with lots of different expertise to work on these different types. So timing of sea ice formation and retreat, duration of the ice cover, ablation, snow accumulation, morphology of the coastal sea ice, all of these different things influence the nearshore Arctic biogeochemical and ecological processes. And then the effects of future change as things are starting to warm up and ice is melting. And we want to look at both the seasonal and interannual time scales as they relate to questions 1 and 2, and then ultimately try to get into some longer term modeling for how we think that the Arctic will change into the future. So the idea is that we want to look at large, globally important rivers, regionally important rivers, including some smaller tundra rivers, and then coastal lagoons, erosional bluffs. And so this is kind of the idea about what we have for the study region kind of outlined here in pink, stretching from the mouth of the Mackenzie over to the mouth of the Yukon River, and then looking at some of the hot spots in between here along the coastal zone, where you get some more inputs of materials into the land. We've had lots of debate about whether we should be focusing on the Mackenzie or whether we should be focusing on the Yukon, or whether we should be splitting our resources between the two of them, or exactly how we need to put this together. And in the end of the day, we've just felt like everything was so important that it wasn't the right time for us to pick. And so, you know, part of how this works is that we put together a scoping study. Eventually there will be a science team that has to put together the final science plan that will decide, I guess, at the relative proportion of how some of these things are going to be studied. The idea is to have intensive sampling and process experiments that are happening all along this coastal zone. You know, sampling from at least one of these large rivers, but also picking out erosional sites, you know, and trying to get some of these rivers that are exclusively draining the tundra. You can imagine all the different processes that we're looking at: primary production, various degradation processes, transformations at multiple scales. Looking for complete seasonality by bringing in remote sensing, although remote sensing is not going to work so hard in the middle of the Arctic winter without light. So then we want to have floats and buoys and moorings and autonomous vehicles, things like that in there, so that we can kind of get an annual or a complete picture of what's happening. Then we also do want to bring in the big boats, and those would sort of involve survey studies going along the shelf to look at the inputs of some of the sort of more open ocean drivers that are in fact impacting near shore processes. Obviously, those are limited to times when it's an ice-free zone: July, August, September, October, things like that. Bringing in satellites, bringing in airplanes, doing sampling from helicopters, doing sampling from small boats, gliders, things like that, big boats, medium-sized boats, things like that. You know, the idea is that the near-shore environment has got a lot of different ways that we need to get after it. And so we want to bring in all the tools that we have in the tool bag to be able to get in there and sample what we need to sample, when we need to sample it. So ice camps, all-terrain vehicles, sleds, some of the things that we just talked about here are all going to come into play when comes time to fully implement Arctic colors. Potential partners. Obviously, there's some links with NSF and NOAA that we can get involved with. USGS has got all the gauging stations for some of the bigger rivers up there, and so we can tie into the USGS. We've got collaborators from Canada, and there's various projects that are involved in Canada that we're hoping to tie in. We were hoping to be able to get better overlap with the NASA program above, Arctic Boreal Vulnerability Experiment, that works on the terrestrial side with a little bit better what's the right word for it? Overlap, with some better overlap with above. It would have been a beautiful opportunity to be looking at what's happening on the land through above as materials flow out into the near coastal zone with Arctic. But, you know, timing didn't happen on that, but that there's still going to be a lot of valuable information that comes from programs like above. Another one that I'll be referencing later on here is the Arctic Arctic Great Rivers Observatory project here that's been collecting data from the 6 major rivers flowing into the Arctic over like the last couple of decades. I guess it's more than 15 years now that program or programs similar to that have been in play. So we envision trying to link to a lot of other different programs here, trying to pull together historical data to get a better picture of what's happening up in the Arctic. This is sort of a notional timeline of how things are rolling out here right now. This is when we started our project basically in 2014, and we submitted the first science plan in 2015. Right now, this RS water quality, that's the project that's funding the research that we're currently doing here, and our project runs out into 2021. And there was a couple different projects that were funded as specifically to do pre-Arctic colors work. So that's the one that I'll talk about in the second half of this presentation here. We're not quite sure yet when Arctic colors is going to roll out. 2023 is probably the earliest that it might roll out, but it could be 2024, 2025. But this kind of gives you an idea about how it will work once it happens. before we ever get into the field work here, there's going to be a phase one kind of more pre-work. So we've got some of the pre-work that we're doing now, but we're thinking about a pre-work phase where we start to build repositories of the data that's already been collected, you know, really trying to pull together all the research that's happened up in the Arctic at this point that's relevant to Arctic colors, and do some of that synthesis work up front so that we have a better base to work from for actually designing the rest of the project here. And so we've got a couple different field campaigns in mind that would span 4 years, with basically 2 years that are intensely in the field. So 1 year ramp up, 2 years in the field, 1 year of synthesis, and doing that in a phase one and a phase two idea, and then having a couple of years of synthesis activities, phase three, that would sort of wind the project down. So we're looking at something that spans about 10 years if you include this phase one pre-work all the way to the synthesis models. So it's not, again, it's not quite clear when this phase one pre-work will happen. And of course, you know, things like coronavirus come along and throw monkey wrenches into anything. So I expressed before a little bit of sadness that we're not going to overlap more with the Arctic Boreal Vulnerability Experiment. But on the other hand, we've got the NSF Beaufort LTER that's come online, and some of the other things that are coming online that we do have an opportunity to overlap with. And of course, PACE is still scheduled to launch in 2022-ish, and that will get some hyperspectral data that we don't have right now from a remote sensing platform. We can get it from an airborne platform, but we don't have it from the remote sensing. So the ability to overlap with PACE, I think, has the potential to be a lot more powerful, with wavelengths that go down to about 350 nanometers instead of bottoming out at 412 like a lot of the satellites that are out there right now. For me, doing a biomarker like lignin, we're of course very interested in those shorter wavelengths. Lignin sort of maxes out its absorbance in sort of the 280 nanometer range, but its influence stretches out to 350. So it correlates very well with absorbance at 350. So this PACE satellite here should give us a lot more capacity and capability for doing some of the biomarkers from space work that I would like to do. So moving forward, at this point here, there's an implementation plan that needs to happen, and an implementation team to devise the science plan that will ultimately define what this final scoping plan will look like, or what the final field campaign will look like. Some contacts if you want to get in touch with any of the Arctic Colors PIs. There's a list of email here, and I'm assuming that this talk is available after this, and so you should be able to come back here and get to some of these email addresses if you would like. And but more importantly, I think, is that you need to send letters of interest to the program managers, Paula Bontampi, Lauren Zoni, and Jack Kay. These are the folks that hold the purse strings, and so the more community pressure, the more community interest that they receive for Arctic Colors, the more likely this is to go, and I think probably the sooner it's likely to go. So if this is something that you think you would like to be involved in, something that you think is important, please let these people know. Okay, so that's the Arctic Colors field campaign spiel. Now I want to kind of transition over into the pre-Arctic Colors project that we're doing right now. And so there's a group of 4 of us working on the impacts processes on delivery of Arctic rivering materials to the near coastal environment. And we're looking at implications for water quality, biogeochemical cycling in preparation for Arctic Colors. So we label this sort of pre-Arctic Colors activities. So I am working with Antonio Menino, Robert Spencer, and Maria Georgiou. And before I leave, I need to give proper recognition to Maria. Maria is the one who's really refined the Arctic Colors presentation that we've been using at many different conferences and things like that too. So I want to make sure that she gets proper credit for all the slides that you just saw. So this pre-Arctic Colors project, one of the things that we're really interested in here is trying to figure out how we take advantage of some of these data sets that are already in existence. And so Arctic GROW has got a good history of sampling from some of the major rivers into the Arctic Ocean, but all this sampling is happening at the head of tides before any of it hits any salt at all. And so one of the questions that we have more generally is, what happens to the river chemistry as you get from the head of tides through estuaries, through deltas, out to that near coastal region? because we can't necessarily just assume that it's a pipe flow from the head of tides out to the coastal zone. We have to consider the possibility that the river chemistry is changing. And so we need to know something about how the river chemistry is changing from the head of tides, where we have this rich data set, out to the coastal zone, the nearshore environment where we want to do the work for Arctic colors. So that's one of the goals of this pre-Arctic project, is to try to look a little bit more closely at the kinds of transformations that happen with river chemistry during transit out to the near coastal zone. We want to, again, as I alluded to before, we want to, this is another opportunity to get a snapshot of current conditions so that we have some markers out there for measuring future change. And so if we get some markers here in 2018 and 2019, when we've been doing the bulk of the field work for this particular project here, that kind of gives us a marker. And, you know, Arctic colors, the field work on that's going to be winding down presumably in 10 to 12 years from now. And so now we have another benchmark that's out there so that we can sort of have something that we can compare and try to get some idea about change. Obviously, it's hard to measure climate change on a 3-year project, because there's just too much interannual variability. You really need to get markers. You really need to get spans of 10 years or more before you can start to make any kind of conclusions about whether change is just interannual variability or whether you've got some climate change going on. And so of course, that's one of the attractivenesses of having satellites that go back to 1997, is that we have an opportunity to try to get a 30-year map of what's happening in terms of Arctic change. And I guess that sort of alludes to number 3, that the part of this project is to start to do some of that work of hindcasting. By getting out into the Arctic environment, by being able to ground truth these algorithms, with the work that we've been doing so far out in the Yukon Delta region, the Norton Sound region here, we have the ability to start looking at some of this satellite data back to 1997, looking at the hindcasting and starting to get that underway. The project is still in the works, so we don't have any stories that are any data sets yet that are complete, but I can give you some pictures of what it is that we've been up to and some little snapshots of the experiments and data that we've been collecting. So obviously the first thing that I alluded to here, Arctic GROW, is a sort of a spin-off from the Partners project that started in 2003. So almost 16, 17 years of data now, looking at flow, looking at chemical constituents coming out of the 6 big rivers around the Arctic. And so obviously for us, the Yukon and Mackenzie data are very important to that region that we've looked at. And so what we're trying to do is to tie this data in from Arctic GROW into that near coastal zone, and we're doing that through some of the research activities that we've got going for this pre-Arctic colors project. And then the leveraging from satellite. Here's a list of the different satellites that have been up in space that are relevant to the kind of work that we want to do with Arctic colors. And here's the one from CWIFS that goes back to 1997. The MODIS satellites are obviously very important as well. And as you just pointing out here, looking at the the nanometer spectral bands here, a lot of them are bottomed out at 412. Here's a 410, a 400, but that's from 2015. 380 from 2016, and then of course PACE here, where it's got this whole band here from 350 on up to 100, up to 800, and so that's really going to expand the capacity of what we can do with remote sensing when we're not limited to just these fixed wavelengths. So another important opportunity here to build and ground truth algorithms that can take advantage of this ocean color data. So this is a snapshot of, this is hot off the press from this week. Blake Clark put together a couple of remote sensing videos looking at the study region that we've been working with. So this is Norton Sound color from space. This is from June 2019. We had various sampling activities that were happening in late May and in May and June of 2019. So this shows you an idea about the ocean color, the Yukon River mouth. Here's snippets of the Yukon River flowing through the Delta region and out onto the coastal zone. So this is the sort of the Yukon Delta region right here. This is the Yukon River south mouth, which is the main channel, that the Yukon River dumps out into the coastal zone. Blake tells me that this is primarily an indicator, at least the red is primarily an indicator of sediments. in the water column here too. So you've got all this water that's dumping out here, but there seems to be a higher concentration of sediment on the north mouth area, looking across over to Nome. Brightness and Brighton Blake tells me that this is total reflectance, all wavelengths. And so I think anywhere where you see this brightness, you start to see some of the impact of the Yukon River on the coastal zone beyond just the sediments here. And you can see that this stretches all the way out into the middle of Norton Sound here, the impact of the Yukon River as it exports. And then looking at some modeled salinity, this also kind of shows you what the plume dynamics look as, you know, obviously you see the biggest plume coming out here from the south mouth, and it extends well out into the Bering Strait. But there's also still a lot of water and a lot of impact here all along the middle and the north mouth region of the delta. So this would be the middle mouth here, this would be the north mouth here. This kind of gives you, whoops. Let's see if I can, how well I can go forward and backward. This gives you an idea about the research activities that we've had going on out here. We've had 3 different field campaigns out to the delta itself. In August of 2018 and May of 2019, and then in June of 2019, collecting samples on the delta proper. Another field campaign that left out of Nome, Alaska, and did a transect across Norton Sound and back, and then ships of opportunity that folks from NASA have been able to tap into as well to try to get some data from this region. And then here's Pilot Station. This is where Arctic Grow gets their data. And Pilot Station is about 120 river miles until you get out to the south mouth here. So that shows you a little bit of the potential for transformation to happen. You can't just assume that this is pipe flow over the course of that 120 miles out to the south mouth, or maybe even more than 120 miles out to the north mouth or the middle mouth here too. There's a lot of opportunity for change and transformation that can happen, and we're trying to capture that. We were working on the delta work. We were working out of the village of Alaknuk. It's a native Alaskan village. This is their tribal council building that we, I guess our primary collaborator was working out of this building here as part of the IGAP program, Augusta Edmond. So we spent a fair amount of time hanging out at the IGAP building, at the town council or the tribal council building while we were there in Alaknuk. A look at some of the local coastal erosion. Most of all the work that we were doing was out of these small river boats. That's Sunny in the background. Who was our driver for one of our drivers on the first trip that we had out here. Mike Novak, you'll see some data from Mike. Ann Kellerman, you'll see some data from Ann out there as well. So this was the first trip out there. Of course, we have to show some moose. Again, Augusta was our primary contact there. I mean, she's been great to work with too. And Sunny was the boat driver that we had on the first trip that we were out there. Some look at the varying landscapes that we're looking at. Tundra in these pictures, for example. And, you know, we don't get a lot of tundra down here in California. So it's kind of an interesting experience to walk out into the tundra and how spongy it is. And I mean, it's like the softest bed you've ever had. You want to just sort of lay down and go to sleep. It's a pretty nice area, but you know, obviously there's a lot of biogeochemistry and a lot of potential for organic carbon sources coming off the tundra into the delta channel. And then there's also other areas that are surrounded by woody plant tissue, alder, things like that. Again, a different kind of organic matter that can potentially be overprinting the Yukon River chemistry signature. Fly over on our way into the delta region. Obviously there's a lot of lakes and meanders and things like that. I mean, it's a geochemical hotspot, and so all these different inputs here with hydrologic connectivity can put DOC into the Yukon River as it passes through the delta. And then, you know, it's also a very big river too, and so you get out to the mouth there and you feel like you're a little bit exposed as you get out to the mouth. And in some cases we were very exposed. We were up to 40 miles off the coast in these river boats, trying to, you know, we had to pick and choose our days when we went there, but, you know, trying to get a salinity gradient and kind of get a more comprehensive picture of what happens to the Yukon River chemistry as it starts to mix with salt water and get out into the coastal zone. So this shows you a hydrograph from the time that we were out there, 2018, and sort of this light blue, that's and 2019 in the darker color, the darker gray. Our first trip out to Alakana was in 2018, and we sort of captured this late summer kind of summer baseline flow condition for 2018. We were back out there in spring of 2019, and so we just got just a little bit before the lead, you know, kind of on the leading edge of the spring freshet. Back out here just on the back side of the spring freshet, and then one more time here in as the spring freshet is declining into its summer baseline flow. So we've been able to capture a range of conditions. Obviously, we didn't get out there in the middle of the winter to look at what's happening, but we were able to capture a range of discharges, a range of conditions. Snow melt, so or runoff driven primarily by snow melt, runoff driven primarily by precipitation, and capturing different types of chemistry. So looking at it sort of from a more top-down perspective, this is data from Mike and Antonio, and it kind of shows you just a rough picture of UV visible absorbance and how much it changes over the course of those 3 cycles. And so if you look at the lower left here on the Yukon South Mouse, this is CDOM plotted from 250 on up to 700 nanometers here. The spring freshet is in red. The relaxation towards summer base flow here is in green, and our what do you call it? The sort of the summer base flow, the summer baseline here is in blue. So I want to see if I can go backward. Yeah. So just as an example here, I mean, you can look at the cross here. The discharge in August of 2018 is pretty similar to the discharge during our second trip to Alaknak here in 2019. So the discharge is similar, but this is coming off the relaxation of the spring freshet. This is after lots of years, or sort of several months of drainage and precipitation driven. So similar discharge, but not so similar optical characteristics. And so we can't just rely on discharge alone as a predictor for what's happening out there. We need to have the seasonality and be able to capture the seasonality to be able to really look at the chemistry. And so you can see here that the DOC during that spring freshet, or coming off the spring freshet, was around 6.4, whereas when we coming to it later on in the summer, it's at about 3.5. So there's different things going on different times of year, and we really needed to be able to capture all of that seasonality. And so the UV visible absorbance is a great way of being able to look at least a first pass of what that looks like. Of course, one of the goals here is to be able to relate satellite data. So looking at 412 nanometers. Okay. And this is sort of scaled to per meter, but being able to relate that to the dissolved organic carbon. And so this is a look at what the algorithm is like over the course of all the data that we collected during those field campaigns. On the right hand here, it shows you what the relationship is during the different types of sampling trips that we took out here. So again, the goal here is we're trying to build these algorithms that allows us to do to tap into the remote sensing data set. Ground truth with what we're finding here on these different field expeditions. And then this shows another thing. So on the y-axis here is a carbon normalized perspective. So this is carbon specific absorbance at 412 nanometers. And I guess the main point that I want to make here is that this red line here shows you a power fit from the mid-Atlantic bight, sort of superimposed over the top of what we've got with our Arctic color data. So the black line here shows you the best fit for the particular data that we have right here now. And the main point that I just want to make here is that we can't take the power fit from the mid-Atlantic bight, for example, and assume that it works for the Yukon Delta, the Norton Sound, Bering Sea region here. That you really have to go there. You have to really ground truth it, get the data on the ground in order to be able to get accurate representations of the chemistry when we start to tie into the remote sensing data here. So that's the main point here, is just to show that every region is unique. and you need to get on the ground and you need to collect that data in order to customize the algorithms that you're using when you're trying to use the remote sensing data. So again, looking for the transformations of the river as it goes through the delta into the coastal zone here. Yes, we have been doing DOC degradation experiments, and this is just one that shows you a little bit of how it looks. Not too shocking that in photo bleaching experiments here that you lose more than 70% of your CDOM at 300 nanometers over the course of 25 days. And of course, there's then the corresponding increase in the spectral slope from 275 to 295 nanometers. Spectral slope, higher spectral slope seems to indicate more low molecular weight DOC. And so, of course, the pretty common interpretation here is that as you are breaking compounds down through photodegradation here, you're taking high molecular weight DOM and breaking it down into low molecular weight DOM. And so this spectral slope parameter here is supposed to capture that breakdown of high molecular weight materials into low molecular weight materials. So Bryce tells me that these two particular plots here kind of look like all the rest of the data, but of course there's a lot more workup that has to come. And then looking at microbial degradation. The blue data here on the left is without any nutrient additions. The red data here on the right is with, or the magenta here is with nutrient additions. And as you get from the darker, more intense colors down to the more light colors, that shows you the progression of the microbial degradation across the, I guess, 250, 450 nanometers here. And this is the change in the absorbance from the darker colors, which is time 0, to the lighter colors here, which I think this is out to 2 weeks, and I'm a little bit fuzzy on the details of what Blake told me he had worked on here too. But the gist of this is that microbial degradation does seem to be nutrient limited. So you add in some nutrients to the system here, and you start to change, and you get more extensive microbial degradation by adding in nutrients. And so this has got some interesting ramifications in terms of thinking about change to the Arctic. You know, anthropogenic activity tends to increase the nutrient runoff into rivers. Anthropogenic activity also tends to increase the DOC runoff into rivers. And so, you know, you kind of wonder which one of those two might win out. You might be putting more DOC into Arctic rivers with more anthropogenic activity and anthropogenic influence. And there is some evidence to suggest that DOC concentrations have gone up by about 10% in these rivers. But if it's also bringing with it more nutrients, it's possible that the two are somehow canceling each other out, at least in terms of bulk DOC. But you can imagine that there would be a winnowing effect there too, where this microbial degradation is selective. And so you still might end up with a net increase of certain types of DOC out to the coastal zone. And so we don't know what kind of impact that might have in the future on the nearshore biogeochemistry. So this is just another angle that needs to be considered when we're thinking about what Arctic colors might look like in the future. Some pigment data collected by Antonio in his shop, and he chose to use very descriptive numbers. So this is just sample stations on the bottom axis here, and everything here is normalized to chlorophyll A. And I don't know the significance of all these things. This is not something that Antonio and I have spent a lot of time talking about. And so I guess the main thing that I just want to pull from this graph here is to show you that the coastal samples are samples 4 through 8. And you can see that there are some different pigments, different ecology that's happening in the coastal zone than there is in the river system itself, the delta proper. I'm going to have to leave that one up to Antonio and others to figure out how to interpret what this actually means and what, you know, the difference between why is there more total chlorophyll C out in the coastal zone than there is in the river itself. I don't know the answer to that. And of course, this navy blue thing seems to be very prominent in the delta as well. So this is from August. Another shot of this during the freshet. And this time the coastal salty samples here are on stations 1 through 5. And again, you can see a little bit of a difference, but it's not so pronounced. And I think part of the reason for that is just because you've got such a high volume of water coming out of the Yukon that it's sort of overwhelming what's happening in the near coastal environment. And we did get out to salinities of 16 as high as 16 when we did this sampling here. So it's not like we're sitting in that 0 to 5 region, you know, where it really would be overwhelmed by the Yukon. So we, you know, we do have some samples that are out to 16. I don't remember if those are 3, 4, or 5, but somewhere one of these stations here is out at 16. This station here is at lower salinity too. So I mean, there seems to be some dynamic, I think, where the salt water or the fresh water first starts to get some significant salt. And that's not atypical, that you've got a lot of action that's happening at that sort of chemical interface, and I guess the pigments seem to be picking up on that a little bit. And then I guess the pet project that I have in mind, and I'll sort of finish off with that, is just looking for this concept of overprinting and looking at the extent to which the delta can overprint the Yukon River DOC signature. So of course we've got lakes, we've got woody vegetation, we've got tundra, we've got meanders, all these different things that are have the potential for bringing dissolved organic carbon off the delta landscape into the Yukon River. And this is sort of a big question. I mean, the Yukon River obviously is a big river with lots of flow. Is there enough carbon coming off the landscape that you could actually move the needle on Yukon River DOC during that 120 miles that it transports from Pilot Station down to the south mouth and to the other mouths? Annual delta runoff, if you do the calculations of precipitation minus evapotranspiration, normalized to the land area of the delta, looks to be on the order of 10% of the annual Yukon River discharge. And so just in terms of a water flux, there, you know, depending on the time of year, when this water is coming off the delta into the Yukon River, there seems to be some potential to be able to overprint it. So again, there's a little bit closer shot of the sampling that we did within the delta proper. Again, here's Pilot Station, 125 or 120 river miles to the south mouth, which is the main channel. It splits here, runs off to the north mouth, runs off to the middle mouth, and then there's a couple of smaller channels here that we also sampled, the Emonic mouth and the Lucknock mouth. And so as a first order, what we can do is just look at the chemistry at the 5 different mouths that we sampled. If it's different, then you can say that the delta is having an impact and changing chemistry. And granted, there's a lot less discharge coming out of the north mouth than the south mouth, but at least you start to, you know, we didn't go out there to specifically design to look at this idea here, but this is us trying to take advantage of the data that we did collect to get an idea about the processing that's happened. So if you look at the south mouth as a proxy for the main discharge and the main stem here, and then compare it to the north mouth, mid mouth, Lucknock mouth, Emonic mouth during the spring freshet, you know, in terms of DOC and SUVA, and looking at some of the DOCs and SUVAs at some of these other mouths, in a lot of cases here, there doesn't look like there's a lot of change. But at the north mouth, you know, we're starting to get in that region where we can start to say that the DOC is significantly smaller, and that which would be indicative of some kinds of degradation processes or removal processes that's happening during transit to the north mouth. SUVA looks to be a little bit higher, and again at the Emonic mouth, same thing, where the SUVA seems to be higher. That's an indication of more aromaticity, more inputs from terrestrial woody materials, things like that. So again, this doesn't necessarily say that overprinting is happening, but it kind of gives you an idea that the potential is there. Looking at that post-freshet relaxation, as we're coming off the freshet into the June, kind of the summer baseline flow here. Again, looking at the main stem, south mouth, DOC and SUVA compared to the north mouth, mid mouth, Lucknock mouth, Emonic mouth. Not a lot of difference here in terms of DOC and SUVA. But for some of the preliminary lignin data that we do have for this time period here, it looks like there's a lot of elevation that's happening. So even though you don't see it in the DOC, even though you don't see it in the SUVA 254, we start getting into these biomarkers here. And so we see some potential differences, some potential for overprinting that's happening in terms of the compositional signature. The lignin itself doesn't look a whole lot different, at least based on syringol to vanillin ratios, enamel to vanillin ratios, but the concentration looks like there might be something going on, relatively speaking. And then of course we've got some potential in delta sources, lakes with higher DOC, lakes, streams, higher SUVA. That kind of gives you an idea about what the potential is there for some of these sources of DOC and water on the delta for overprinting. And then if we go back to the summer base flow again here, looking at the main stem and Suva. The one that stands out here the most during the summer is just the potential for bulk DOC overprinting. The Lucknock mouth is elevated, the Emonic mouth is elevated relative to the south mouth and the main stem. And then you start to look at the DOC at some of these in delta sources that we looked at, 3 different lakes in a stream with DOCs ranging from 11.8 up to 48. Suva's ranging from 3.5 up to 5. And you can imagine that it doesn't take a whole lot of water coming out of streams if a DOC is at 48 and a Suva is at 5 to start impacting the chemistry of the river itself. And then I guess one more example here, looking at mixing lines across the salinity gradient, DOC in red, Suva with these hash marks here. And the mixing lines that I've drawn primarily here are from the south mouth out to the highest salinity. I put in an extra mixing line here that looks at the higher DOC mouths during the summer baseline here, but the main stem, the south mouth, is this lower mixing line. So you don't see a lot of evidence for DOC. I mean, a little bit of evidence for removal here in terms of DOC during the summer baseline. When you look at Suva 254 on the mixing line compared to the data there, you see a lot of evidence for removal, and that would be consistent with summer intensity of the sun, photooxidation, and removing aromatic compounds, higher temperatures, spinning up microbial degradation, things like that. It would make sense that you would expect to get a little bit of degradation happening in the summer. Looking at the spring freshet, maybe not so much opportunity there for degradation, in part just because the water is moving faster. There's less time for these processes to happen. So looking at DOC, maybe some evidence for removal here in these mid salinities. But Suva is flipped here, and now if anything, it looks like there's higher aromaticity coming into the river water as it's mixing out into the plume. So in summary then, just kind of a teaser of the data that we have, it looks that this degradation and overprinting of DOC within the delta is real, but it seems to be, you know, certain times in certain places, and that's something that we're going to have to look at more and characterize more now that we know that there's the potential for it. There's the potential to put out a study that does a better job of looking at it and trying to characterize it, specifically geared toward looking at those kinds of processes. Still to come, we have arranged with our local collaborators, Augusta, and we have the Arctic Grow has still been collecting data here too. And so we've been trying to get a coordinated sampling from Pilot Station and the south mouth near Lucknock, with a lag time about a week that accounts for the 120 river miles between the two. And so the idea is that instead of just trying to speculate on the transformations that are happening, we want to try to measure it more directly by collecting a sample at Pilot Station, a week later collecting a sample at the south mouth near Lucknock, and just comparing the two directly so that we can see directly whether these transformations that we're speculating are happening are ongoing. And so we've got this that's happening about every other month. We're trying to collect these paired samples to be able to look at that transformation. Obviously, a lot more work to do on lignin analysis, a lot more work to do on FTICR, MS analyses. That's happening out of Florida State with Rob Spencer and Ann Kellerman. Salinity mixing experiments. You know, we don't have the ability to go out there anytime we want to and get transects across the salinity gradient. And so we've been working in our lab to try to take water from the head of tides, doing simulated experiments within the lab to see how the water chemistry is changing. Data that I didn't show you at all from the North Shore on the LTER samples. Last summer, there was a couple of different research activities getting out to the LTER, working with Jim McClellan to collect data. I didn't show any of that today because, frankly, I couldn't interpret what they had yet. It's not my data. I don't want to sit here and babble about things that I don't know. So I chose to not show that data for this particular topic. We've got some Mackenzie River samples that are coming in from these Arctic Rogue data and that we want to run through these salinity mixing experiments as well. Obviously, full development and refinement of the remote sensing algorithms leading to the hindcasting. That's all stuff that's still to come. And so then finally, I just want to thank you again for the opportunity to give this talk. It's the poster that was sent to me from the cleanup crew. As you can imagine, there's a lot of trash that comes down the river in the springtime, and so the Aluknuk IGAP program there sends an armada of kids out to the river to pick up all the trash every year, and so they send a nice little thank you poster to me here for contributing to those efforts. And so I'll say thank you to everybody who's been listening, paying attention, and I guess that's it.
Terrific. Thank you very much, Peter. We do have a couple questions already in the chat. One is from, I apologize for mispronouncing your name, Chiking Zhang. Says, thank you, Peter, for the great presentation. A lot of interesting work. What is the instrument method used for freshet pigment measured?
I mean, it's all done by HPLC, so I don't know if that's as specific as what you were looking for, but it's sort of just the classic extraction and then analysis by HPLC.
Great. Does anybody else have any questions you want to, they say thanks. That was the answer to their question. If you have a question, you can unmute yourself and ask Peter directly, or you can type it in the chat if you're hampered with audio. Any questions?
It's been my experience with the Zoom stuff. I mean, certainly giving lectures and things like that, I get a lot less questions, a lot fewer questions from students that I've been teaching. I have to say that I really miss the interactions with the face-to-face interaction with people during this lockdown thing. It's makes giving talks a lot more enjoyable when you've kind of got that immediate body language feedback and questions.
Right.
Peter, this is Steve. Quick question, or a couple quick questions. Thank you so much for the talk. This is fascinating stuff. I see all kinds of possibilities or other research questions in this, and it's exciting. Exciting material, and I'm interested to follow this project into the future. One simple question was, what are the sizes of these rivers? I'm not even sure. I mean, is the Mackenzie and Yukon, are we talking Mississippi River size, or does it have larger fluctuations than, say, rivers in the lower 48? I know there was one slide which had somewhat of a hydrograph on it. I didn't really catch those numbers.
Yeah, unfortunately I don't do a very good job of translating back and forth between cubic meters per second and cubic feet per second. The Yukon River dumps an awful lot of water in there, and I don't know if it's on the same scale as the Mackenzie. I'd have to do a quick Wikipedia search here to see, or sorry, the same scale as the Mississippi River. But I think it's getting close.
Yeah, I think so. And does the project moving forward, it seems like you talked early on about just the Yukon and the Mackenzie, but is this in the context of all the rivers of the Arctic? I mean, will there at some point, I know you talked about previous work had, centered on all the inputs. Will your work just center on the North American, say, inputs?
I think at this point that's the focus. That's where NASA, I think, is sort of well. I mean, I guess there's two parts to that. One is just that, if you start to imagine what this would look, when you start to imagine the range of activities and the amount of money and just the logistics of getting to the Arctic. I mean, just even proposing what we want for the Yukon and the Mackenzie, I think when we put together our budget, we were looking at something like $80 million. I mean, the likelihood that we get $80 million from NASA to do what it is that we were proposing to do doesn't seem very likely. And so, there's likely to be some de-scoping that happens with the implementation plan to try to get that down to a price tag where they're more willing to do that. And so when you start thinking about just that, being able to stretch funding and being able to fund something that goes across the entire Arctic would be just too much. It would be too much for NASA to be able to take on. And obviously, there would be a logistical piece to that too that would be really challenging to do. And so I guess what we're hoping for is that it's collaborations. Where we've had a lot of discussions with folks up in Canada trying to, and the possibility of trying to extend farther east from the Mackenzie River along the Canadian border. And so if we can get those kinds of connections and collaborations with Canada, we at least have the ability to work with that. And so I guess that would be the same goal, I think, for trying to incorporate some of the Russian rivers. I mean, I think that also kind of tells you a little bit about how likely it is to be able to expand into those rivers there too. I mean, the whole dynamic that we have in terms of interacting with Russia is not great right now. And so I think a lot of the research that's happened in Russia has been sort of channeled through Germany. And so then that means sort of having to collaborate with Germany and Russia to be able to pull those things off. So, I mean, at this point, it just seems like logistically, politically, financially, the barriers to be able to do something comprehensive across all 6 of the great rivers or the major rivers doesn't seem very likely. So I think at this point here, we really have to focus in on just what we can do with the North American rivers.
Sure. Okay. And just a final, more of a science question. I was really fascinated by the DOC work and the values and the characterization of the DOC material. There's been quite a bit done here in the Midwest and our northern Wisconsin lakes and in Minnesota and of course in Canada, and how DOC values have changed. A lot of DOC work was done back in the acid rain days, and we've seen this brownification of lakes, if you will, both here and in Canada. It's been pretty widely documented, as in Sweden and places like that. And I'm wondering, you kind of alluded to anthropogenic changes impacting, both the hydrograph and the DOC material. Were you referring to climate change impacts, or are there other, say, land use, land cover, things going on in those regions, the drivers of this change?
Well, I think the primary drivers primary driver is going to be climate change, just in the way that it impacts the seasonality of the runoff, and the potential for maybe getting a longer growing season and more primary production. I mean, I'm not an ecologist, and so I don't want to misspeak here too much about the different ways that you're going to get succession that's happening up there. But I mean, one of the things that happens when you start to thaw out the permafrost in the tundra is that you start to get more woody plant encroachment. And so you can imagine that you're going to get a different kind of DOC that's coming off of a woody plant landscape than you are off of a tundra landscape. So that's an example of a potential change. But then you also start thinking about these massive fires that have been happening up there. And so, climate change is probably facilitating those fires, but it's the fire itself that's changing the vegetation and changing the landscape that's going to change what runs off. And I mean, just in general, anytime you've got a lot of disturbance on the landscape, you tend to increase the DOC, you tend to increase the nutrient release from the soils. You tend to make your system more flashy. And so I guess those are the kinds of changes. And I think all of it sort of starts with climate change, but the climate change leads to other more, I guess, first order processes that are kind of having more of the direct impact. I mean, in terms of, so like DOC runoff, there's been a lot of speculation that this increase in DOC runoff would be coming from permafrost DOC, but the research that's been conducted so far seems to indicate that this permafrost DOC that's released is so labile that none of it really makes it out to the coastal zone. It seems like it primarily degrades. And so if that's the case, then where is this increase in DOC coming from? Well, one of those answers could be from the woody plant encroachment, for example. Woody plants putting out compounds that have a little bit more resistant to degradation and can make it out to the coastal zone. So there's a lot of those different things, and again, I'm kind of out of my, I'm out of my lane, I guess, when I start speculating too broadly on what's happening with the ecology of the landscape. But we do know that but changes in ecology have a direct impact on the DOC concentrations and compositions and nutrients as well.
Okay, thanks.
All right, any other questions? We do have one in the chat from Catherine Kuhn from the University of Washington. She's curious if there has been any hyperspectral airborne imagery flown over these sites.
Well, any. I don't know the answer to any. I would say that there's been little, and maybe none. I don't know. I don't know the answer to that. I mean, it's an interesting question. So we put in a NASA EVS proposal, Earth Venture Suborbital proposal, specifically to do that. And so we were trying to get funding to do airborne sensing from, I guess we were from the Mackenzie Mouth over to Utkavik and kind of in that region. And so that's something that we had proposed to do, is to get in to get the airborne sensor. And our plan is to put it in again. I guess none of the Earth Venture Suborbital proposals that have ultimately been funded got funded on the first round. So we've only put it in once. And so we're going to try again, see if we can get in the airborne sensors. And of course, for Arctic colors, we would also be hoping to be able to get in some airborne sensors as well.
Great. Any last questions? All right. Well, thank you very much for your exciting talk today, Peter. We were pleased to host you. The recording will be made available sometime within, like maybe by the beginning of next week, since it's Friday and the weekend is imminent, on the GEO AquaWatch website. I'll place that website in the chat. And we hope everybody will also tune in for the next webinar given by Joe Salisbury about Glimmer on May 21st.
Joe is one of the PIs on the Arctic color scoping project here too, so that's doesn't surprise me.
Well, thank you very much, everybody. In the chat is the website. Choose resources, and then you'll see all the future and past webinars listed as a drop down underneath the resources. And have a great day.
All right, thanks again for the invitation.
Thank you. Thanks, Peter.
So Steve, you can stop recording, and then I'll send you an email about how to get me the file.